Okay, this is the last slide that we stopped on. And so now we'll continue and get into the specifics about how to design the logic. As you remember, there's two important kinds of logic that are different. A combinational logic, where the output now depends only on the inputs now. And sequential logic, where we have state information, we have storage. Okay, remember those? And registers would be examples of sequential, and an ALU would be an example of combinational logic. And so here's a little 1-bit ALU. Can everybody see that? It gives us the ability to and to or, and to add, and if we do the carry in right, probably to subtract A and B. So we've got some operations, and we'll decide which one we want. Do we want to get that one, or that one, or that one, based on the ALU up thing here. And so this is a single bit. You know, the A and B are 1-bit quantities. If you want to make a 4-bit ALU, you make 4 of those. So here's the lowest bit of A, the second lowest, the third lowest, and the highest bit of A and B, going into each 1-bit ALU. And the result values, when blocked together like this, see the shape of the ALU? It's really just a bunch of little ALU, 1-bit ALUs, inside it. Now, of course, one problem with the carry is we get, as you see here, ripple carry. The output of this is the input of this, the output of this, the input of this. So that's going to be a slow carry chain for addition. We'll have to speed that up somehow. But functionally, this will work. So the idea of how to do ALU is 4 bits of A, 4 bits of B. You select which operation you want here, and you get some combination of operations from these individual 1-bit ALUs. Okay, now, you don't need a full ALU to do addition, do you? So if we just want to add, we strip out all the other operations and just take 32 bits of A and 32 bits of B, have a carry in and a carry out, and you get a 32-bit sum. That's an adder. You could have a full ALU, then you need op bits to say, what do you want it to do? Add, subtract, multiply, divide, shift, and, or, NAND, whatever you want. You know, you give it opcode bits. Here's A, here's B, there's the result. Maybe we have a little special bit that tells us if the result bits are all 0, this goes to 1. A big NOR gate would do that for us. Then we'll know if our result is 0. And that's a useful one because when we subtract, a way to test for equality is to see if the result is 0. And then you don't have to check all these bits yourself. You can just see if the 0 bit is set to be 1. Okay, those are some combinational elements that we'll use. Oh, there was also multiplexer on here. Very common in Datapath is choose A or choose B according to this bit. One of them gets through. The other one, it's a switch. Multiplexers are switches. They're selectors. That's the other name for them. You select one of the inputs and block the other. I know you know all this. I'm just doing a quick review of some of the hardware we learned in CS-224. Now, let's go to storage elements. We begin with the simplest kind, which is a latch. And you take a simple SR latch like this and modify it, and it becomes a D latch when you put some gating on the front. Remember, latches are the fundamental building blocks of flip-flops. One way to make a flip-flop is this master-slave approach. Here's the master latch, here's the slave latch. We have a clock which is inverted, goes to them at opposite phases, and so you can guarantee that this will store a bit and doesn't have transparency, which we can't, that'll cause us to have feedback loops and oscillation. And if you take a single flip-flop and you make it a one-dimensional vector, you have a thing called a register. And a register is just a set of n flip-flops in parallel. Here's an n-bit input. The least significant goes to this flip-flop, the next one goes to this flip-flop, so on, and the most significant one goes to this flip-flop. And the flip-flops all share common timing. They share a common clock, and they also share a common write enable. So you're either able to write everything into this set of flip-flops or nothing. And the set of flip-flops is called a register. So that's our next step up. So from a zero-dimensional storage, 1 bit, now to a one-dimensional storage, a register. And of course, if I take these and show out them, I have two-dimensional storage, an array of bits, which would be like memory. Okay? Notice that we're going, for the register, we'll say a couple of things. We'll have a write enable signal that lets us not change it when it's low and change it when it's high. And we'll have our clock be common. Everybody here see that it's an edge-triggered flip-flop, active on falling or low falling edge-triggered flip-flop. Now, if I take a set of registers and show out them, bang, 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 I have a thing called a register file. If I do thousands of them, I call it a memory. Okay? But a register file is just a small memory. Everybody can see it's two-dimensional. Every register holds 32 bits, and there's 32 registers. Okay? Well, that means that you have to say which register do you want to read from, which register do you want to write from. You have to give it addresses. And so we've got a 5-bit signal for the register you want to write into, and a 5-bit signal for the register you want to read out from, and another 5-bit signal for a different register you're going to read out from. So it's 2 reads are possible at the same time. We call that a 2-ported memory. 2 read ports, 1 write port. Okay? In other words, I can write one thing and read 2 things from this memory in a single clock cycle. Okay? In one operation or one timing period, I can do 2 reads and a write. And that's exactly what I want to do, isn't it? The R-type instructions say, give me 2 register operands, do something with them in the ALU, and store it back before the clock is done. That's what we want to do in an R-type operation. It's a register operation, full register, both register source operands, do something with them, add them, shift them, subtract them, OR them, and stick it back in the register before the clock cycle finishes. So that's exactly what we need. Read out 2, telling me which one's here and getting them here. Do something with it, bring the result and put it back here. When the clock says go, you tell it where to write it, and it's done. And it writes back in, all in a single clock cycle. Any questions about that? That's a useful thing. We could do the same with this. The trouble is I can only do 1 read out from it and 1 write on top of it. I'm forced to change it. If I do a single read and a single write, it doesn't stay the same. But with this one, I could read register 1 and read register 2 and write to register 3, so 1 and 2 stay the same. And I changed a different one. Okay, so this has more flexibility, and of course it also has more registers. Any questions about the register file concept? I think we had that actually. You can see the implementation of it in the CS-224 textbook and on the slides. It uses multiplexers inside it to decide which of the 32 goes out on that bus. You got to have a multiplexer. To decide which of the 32 goes out on that bus, you have to have a multiplexer. To decide which of the 32 this goes to, we have to have selecting and enabling and use a decoder for that. Okay? So this write signal doesn't allow them all to be written to. That would be foolish. It allows only one of them to be written to, and you say which one with this here. So that's 5 to 32 decoding. The 1 hot will tell along with this the particular register, hey, it's you this time. We're going to change your value. Get ready to write a new value, and it's going to come in on this data bus. Okay, so this gives some more information about it. You can see here about the clock an interesting thing. I should make this clear. The clock input doesn't matter and makes no difference at all if we're reading. If we're reading, that behaves like a combinational circuit. Give me the values on RA and RB as inputs, and I'll give you the values on bus A and bus B as outputs a short time later. We don't care about clocking. There's nothing clocked about that. It behaves combinationally. We use the clock signal for write timing. We know that we have to get the values set up and stable on all of these before the clock edge comes in order to be able to do a proper write, because it's a register that we're writing to. And registers have those kind of limitations. Remember setup time, hold time, all that stuff? Yeah, we talked about that. So that's the point. RA or RB have to be stable, and they will be on reads a short time after the access time. It's a minor simplification of reality, but it's reasonable to think of this register file as combinational when reading, but sequential when writing. That model will help you to simply understand it more simply. Okay, let's make it bigger. Let's don't have 32 locations. Let's have thousands, millions, billions of locations. Well, now we just call it memory, okay? But at every location, there's a 32-bit value stored. You might say that sounds like a really, really, really big register file, and you would be right if you were to say that. We don't call it register file, but register file could be thought of as miniature memory. Full memory could be thought as Kojimon register file. It's not wrong to imagine it's just a matter of scale. Now you'll notice this memory, though, is not a 2 read port, 1 write port memory. It's a 1 read port, 1 write port memory. Everybody see that? Okay. And in fact, the address is not different, it's shared. So either you are reading, and this is the address you're reading from, or you are writing, and this is the address you're writing to. So now this is different. This memory can only do one thing in a clock cycle. Okay? Only one thing. You want to do a read? Great. Put the address you want to read from on the address bits. You want to do a write? Put the address you want to write to on the write bits. How come we don't say how many bits this is? because we didn't say how big the memory is. How can we be so sure that this is 32 and this is 32? Yeah, because it's 4 bytes wide. So the memory words are 32 bits each, but we don't know how many there are. If I tell you this is a mega byte of memory, how many addresses will I have? Careful, megabyte. How many words? 256 kilo words, right? 2 to the 20th is the number of bytes, but 2 to the 18th is the number of words. So therefore, I would have 18 bits here to address a megabyte, or 256, no, I'm sorry, kilo words. Sorry, I'm saying it wrong. It'd be 256 kilo words, or 2 to the 18th, 18 address bits. Okay, again, the same thing here. Look at this. The clock input is a factor only for writing. We're going to make a minor simplification of reality and say when reading, it behaves combinationally. Give the address. A little while later, the data you want to read has popped out on the outputs. Okay? So we're going to think of it as combinational for reading, but sequential for writing. That will help us to model this. Okay? So that's a memory block diagram. Much simplified over the detail we looked at in CS-224. Remember that? A whole chapter just looking at how they're organized on the inside. Now we're up from that. We've abstracted up. We're at a level where we say, that's what it looks like, that's what it does, on we go. All right? I'm not interested in the decoders in there. I'm not interested in the cell technology. I'm not interested in the layout of the array. That's it. That's a different level. This level is just behavior of the memory system. Are we together on that? Okay. Now, you can go down to that level and work on the detail of how many chips is that and what are the buses organized and tell me about the timing. But this is the master block level of the memory system. Okay? All right, good. It's good to have that ability to scale up and down and to abstract when we need to. Okay, so you can see that if I want to do a write, I set the write enable bit to 1. If I didn't, I'm doing reading. Now, let's review a little bit of logic design. I think everybody remembers, at least in my sections of CS-224, we worked hard on timing issues. We worked hard to understand this kind of a diagram here. Here's a register, and it's got some data. And that data is going to flow through this combinational circuitry, and it's going to be transformed and create some new values here. And those new values will be locked into, or latched into, or recorded into, or cont'd into this register. So we call that a register transfer. And it has to happen in one clock cycle. So if I'm triggered on the falling edge here, then on the falling edge here, I'm going to be triggered as well. So in one clock cycle, I need to get all that to be done and be in here. Well, can I? Is the clock cycle long enough? What kind of things have to happen in one clock cycle? I think you can see. From the time the clock comes here, whoa, that says this data gets latched in and is put on the Q outputs. We call that clock to Q delay. Some time for the circuitry here to put it here. And then there's some delay here through the combinational circuit. In fact, the one we're interested in is the longest delay. If this one gets here quick, but this one's still delaying, then it's this one that's my problem. Because I cannot have changing signals here when I clock it. They have to be stable and good boys all lined up like soldiers. So I've got to therefore look at the slowest path. That's the one that determines my combinational delay. And then, you know what? When they're all here lined up, they have to be lined up early. Before the comaton comes out, it's not enough to just step into line right as he comes to your place. You've got to be lined up early because these flip-flops have something called setup time. And they don't work, they don't latch properly in if you arrive right at the last minute. Yes, sir, you have to give them a little bit of advance stability. Okay, so the signals all have to be stable, and then the setup time says, we're all ready, sir. Hi, comaton. You may now do the inspection of the troops. And then the clock will latch it in. But you know what? This clock signal and this clock signal are not guaranteed to be absolutely at the same instant of time. There's something called clock skew, which has to do with distance the signal wavefront travels and resistance, capacitance, and inductance on that, and loss. Therefore, there may be a slight difference in time between this and this. I have to factor that in too. It's called clock skew. Now, some of you, this may be deja vu, because one semester ago we had the very same talk with a very similar slide. This, my friends, is the fundamental business of digital engineering. And if you don't understand this, you're never going to be able to design any digital circuits. You've got to get this right to understand how digital circuits are going to work properly. This is clocking 101. It won't work unless you do this. So we can see that the cycle time needs to be greater than or equal to this sum of things. If it's greater than this, no problem. It means everybody's ready, we're all waiting. The commandant didn't come, but we're ready at least. But if it's shorter than this, it means that you took garbage and you latched it in before it was stable, and the last soldiers didn't get there, but it's too late because they're already latched in. And you got a wrong value, and you're now going to send that wrong value on down for further computation. No chance. You're done. Bish bitti. You cannot get a correct calculation if you do not meet this equation. Your circuit can't work correctly. This equation here in red is the fundamental equation of digital design engineering. You got to have that on the physical level or nothing's going to work. You could take all the theory courses you want all day long and pass all the truth tables and Carnot maps. It doesn't matter. It's not going to work unless you do this. This is applied engineering. That other stuff is theoretical, okay? You got to have this working on the circuit level. Otherwise, it isn't going to work. Okay, so that's the next thing that we have to understand is that. Okay, now read this. Timing will always work if the clock is slow enough. Sure. Who wants slow clocks? Raise your hand. I want slow digital circuits. That's what I like. Nobody. Everybody says, crank it up. How fast is it? Let's make the clock shorter. We know performance is determined by clock cycle time. Let's make it smaller. Amma beli biarakadar. Smaller amma with this limit. Can't be too small. Clock cycle time can't be too short. If you start to pull this in, oh no, we didn't make it. So your system will not work if you make the clock cycle time too short. Another way to say it is, the design engineering you do here will determine your minimum cycle time. Okay? Now, I think, though, that everybody should be able to see pretty quick, well, Hoja, what if I just did half the work and put a register right here, and then I did the second half in the next clock cycle? Wouldn't I be able to have 2 short clock cycles instead of 1 long one? And the answer is, affair coachum. That's exactly right. You would. You would have a high clock rate, but what did you do to your CPI? Uh-oh, what was 1 clock cycle is now 2, but the clock cycle time got short. It's a trade-off, isn't it? Can you see how? That would be a multi-cycle implementation of the same thing right now. It's a single-cycle implementation. Okay, there's trade-offs involved. Yes, I can pipeline it. I can put a register right there. That's called pipelining. So do part of the work, and then do the rest of it later. It has its upside and its downside. Okay, now we're ready to move on into how to, yeah.
Can you explain a little more about cluster?
About what?
Cluster.
No, we did that in CS-224. That was where we worked on the circuits. I'm sorry. I think I've given adequate explanation here, and I got to move on. So talk to me after the class. We can go into that. I'll take you back to the book, CS-224, show you where that was. I'd be happy to, but not in front of everybody to do it again now. It's just not efficient. Sorry. Okay, that was a review of what we hope you learned from CS-224, especially that business about the red equation being so fundamental and important. So, if I didn't, I hope now at least I did, okay? That's a really, really important thing. You can't work without that. I don't care what your theory and your kernel maps tell you. Nothing's going to work if you don't obey that. All right, now let's get back to implementing our ISA in a processor. Let's design a processor. Okay, remember, what we've got to do is we've got to fetch. And fetching says, from memory, give the PC as the address and get out the value, okay? And we also need to update the program counter. So the PC value gets 4 added to it, and that becomes the new PC value for any sequential thing. Now branching and jumping would be a little different from that, okay? So here's our fetch, and here's our update the PC. And those are written as register transfer operations. So that means that we need hardware that does this. Here's my instruction memory. Here's my PC. The PC goes to it, and out comes the instruction word. But the PC also goes to an adder where it gets 4 and becomes the new PC on the clock edge. Okay? So PC update and fetch of instruction are done with this hardware. Are there any questions about that hardware? Okay. Let's go on. All right, now the next one talks about the add instruction. And the add instruction looks like this. And what we're going to do is turn it into register transfer language equivalent. So does everybody agree that this is done by this? Fetch the instruction out of memory. Use the RS part to go get something from register file. Use the RT part to get another something from register file. Add those two somethings and put the result of that addition into the register file in a place that RD tells you to put it, and be sure that you update the PC when you're done, or somewhere, maybe early, maybe late. Got it? Fetch it, decode it, execute it, get the address of the next instruction. To me, that looks like the execution cycle. Go back a little bit. I think that basically is exactly this. Result got stored, did the execution, got the operands, decoded the instruction, fetched it, and figured out what the next instruction was going to be. Okay, so there we go for one instruction. We just did it for the add, but it's not that scary anymore. Is this register transfer language? Is this register transfer language? Is this register? Yeah, okay. So we're using RTL. This does this. So remember what we said? The first step is take every one of these and translate them into this. Second step is figure out from all of those what you need for hardware elements. Okay, go on. Subtract. There it is. Does this. Not much different. Only one little place is different. Are we good? Okay, let's go on. All right, now let's look at this one. Let's realize what's going on here. Get the value from register file that RS tells you. Get the value from register file RT tells you. Do some operation on it and store it in RD. That's a general formula for what? Every R-type instruction. The only thing changing is the op. Did everybody notice that between subtract and add, there was a kind of a funny similarity? Look at the only thing you see. Watch those two slides. The only thing you see changing is that little plus there and that little word there and the thing on the top. And you know what? OR would be the same, and shift would be the same, and, you know, they would all be the same. Yeah, right, of course. To do subtract, you need a code here that's different than doing add. The function code has to be different, otherwise you'll do the same operation. Okay? So that's interesting. Just want you to be aware of that. Now, that means that to do any R-type, I need this hardware. I got to get the two operands out of here, addressing them with 5-bit values and getting those 32-bit values, send them to the ALU, and do the operation on it, whatever the op is. Add, subtract, or, and, shift, whatever. And then take the result and send it back around, and on the clock write it in to the place that the RD register tells you to write it. And set the reg write signal to be true. That's the hardware to do R-type instructions. Okay? Any comments about that? Any questions about that? Is this okay? I'm not losing anybody here? Hope you're understanding what we're doing. So where did this come from? The instruction, a certain bit field. Where did this come from? The instruction, a certain bit field. Where did this come from? The instruction, a certain bit field. Where did this come from? Not sure yet. Some kind of control. We don't know. Reg write. I don't know. Where did this come from? Somewhere else, the clock. Where did this come from? Not the, okay, so some things are direct from the instruction. But I think you can see, there it says those are direct. There's some other things here, and we're going to call those control signals, or in some jargon, control points. And they're going to have to come from a circuit called the control circuit, or control part of the processor. So while this is data path, there's things coming into the data path from a different place called control. Can anybody tell me what the ALU and reg write signal need to be if this is a subtract instruction? If it's a subtract instruction, this needs to be 1, and this needs to be the code for subtracting. Okay, well, how do I know if it's a subtract instruction? How do I know if it's a subtract instruction? Yeah, the 34 here, it tells me it's a subtract. What if it's not 34? What if it happens to be 32? Yeah, then I want to do what? Here and here. What do I want to do now? High and the code for add. Of course I want to write something in there. What if it's a branch instruction? What should the code for here and here be? Branching, does it change any values in the register file? No, that needs to be a 0. I don't want to do any writes. But what does the ALU operation need to be if I'm deciding about equality between two things? Subtracting code, yeah. Okay, do you get how it's beginning to work? The code for the instruction will tell these kind of control signals what they need to be. That means there's going to have to be a control circuit with some things coming in and these kind of things coming out. These come direct from the instruction, no problem. But these don't come direct from the instruction. Okay, so you may get to feel how it's going to work. Let's look at the OR immediate. This is a I-type instruction, so it's going to be a little bit different, isn't it? OR immediate takes an immediate field, and what we want to do with that immediate field is zero extend it, because it's a logical operand. If it was a add immediate, I would not zero extend it, I would sign extend it, because it's not, it's a number, and I got to preserve its sign. But in this case, it's not a number, it's just 16 bits, and I need to make it 32 bits. So I extend it. That's a 32-bit number, that's a 32-bit number. I OR them together, I put my result in, register file, RT. Fetch first, add 4 at the end. Are we good? Where do I get the value of RS? Right out of there. Where do I get the value of RT? Right out of there. Where do I get the value of immediate? Right out of there. Where do I send this OR signal to? Right there. How did I know I'm supposed to OR it? How did I know I'm supposed to OR it? Comes from here. The code for OR will be stored right here. So that's going to go to the control system, and the control system is going to turn that into, go back, and then into, make that an OR and make that a write. Exactly. Okay. All right, let's go on. So the immediate ops need something like this. If it's a logical immediate, I need a zero extender. I take the immediate field of 16 and turn it into a 32-bit. I have a mux here, and I'm going to choose, do I take the second operand from here or the second operand from here? And obviously this mux will choose the ALU source to be here when it's R-type and here when it's immediate type. Shall I say that again? This mux chooses. It says, what should the second source for my ALU operation be? The first source is going to come out of register addressed by the RS field. Okay, so RS is my first operand. And my second operand could be RT. But in I-type instructions, RT is not my second operand. It's my destination. Therefore, what's my second operand in immediates? Comes from here. That's my second operand. So zero extended if it's a logical, or sign extended if it's an arithmetic, and then choose it in the mux. The mux has to choose. So you know what this is going to be? Choose this one if it's R-type. Choose this one if it's I-type. Yeah, yeah, yeah. What is this thing here? Another control signal coming from my control unit. Slowly I'm beginning to accumulate a bunch of control points. Now, why don't I care about RT? Why don't I care about RT here for the second source? Because I'm not going to, whatever is here, I'm not going to take it anyway. But I want you to notice that I do want RT to be the destination address. So therefore, it's not enough to just send RD here. I need to send RT here. I need a mux to choose. So what's going to go on here? Register destination. Choose RD when it's R-type. Choose RT when it's I-type. Yes, exactly. Okay. All right. So that's why I need those muxes, and that created another control signal or control point. All right. Any questions so far? Now we're going to get into memory. We're going to do load and store. So far we've just done arithmetic and logic, either the full R-type or the immediates. Now we're going to, as you can imagine, go to load and store and then branch and then jump. And then we're done. So I've got 15, 20 minutes left. That's what my intentions are, is to do that. But I don't want to go there unless you're good. Are you good? Emerson. You know what that means. Anlatabildim mi? Yani jeton düşüyor. Yok hoca düşmüyor, takıldı bir yerde. All right, come on. Be honest with me. Can we go forward, or you want to go back and do some review here? Do we need to go back and look at it again and talk about it some more? Özer Bey, hak size vereceğim. You're good, all right, he's good. Okay, glad. Ozer's good. Sanem Hanım, are you good? You're good, all right. Okan, are you good? What? I think we can stop here. Yani erken bırakayım mı? No, we're going to go on. We're going to go on unless I hear somebody that says go. It's not stop here. It's either go back or go forward. But we're not going to. No, it's not enough. We got to do load and store and branch and jump. Okay. All right. All right. So buckle your seatbelt. Get ready for takeoff. This is your captain speaking. We'll be flying at an altitude of 12 million miles. All right, here we go. This is the load instruction. It looks like this in assembly language. So now in register transfer language, what do we have to do? Well, obviously fetch it, and then obviously calculate an address, and that address is what? The base address that you got out of the register file, and sign extending the immediate, add those two together, and that's the memory address. And what do you want to do with that memory address? You want to go to memory with that as the address and read something and put it into register, the RT register. And when you've done that, you've done the load. Just be sure that you change the PC. Okay? Now, if you look carefully, that's the same, that's the same. What used to take one line takes two now, but it doesn't have to. Can everybody see that address is just here? I could put all that inside there and do it in one line. Got it? It's just broken up for, simplicity of understanding. This goes to there and keeps on going. So I could stick that whole expression in there, but it's not done that way. It's not written that way, just so you don't get confused. But calculate an address and use that address to fetch from memory. Okay. So, if that's what we want to do, we need to add some more to our data path to do it. What's new here? Look and see what's new. The red stuff. Oh, you're so clever. The red stuff is new. So that's all the same. But look what happened here to our extender. Our extender now takes 16-bit immediates, but it doesn't always zero extend. Now we've got an operator. Zero extend me, sign extend me. Okay, so depending on what kind of extension you need. Great, same here, same here. We get our two operands here. So here's the base address here, and here's the sign extended immediate coming here. Add them together, and you've got what? The final result? No, you've got the memory address. What are you going to do with that memory address? Send it to data memory and tell it not to write, please. And so a little while later, you're going to get out the thing that you read. So here we've now got out the value from data memory that we read from that address. Remember, it's combinational. So really, this doesn't do anything. That's about writing, and we're not writing. We're reading on a load. So we get it, and now I need to do what with it? Send it back to the register file. So it means it has to get through this new multiplexer because we were already sending those back, but now there's this, and you cannot just merge two buses together. Everybody knows that. You get a short circuit. You did that a few times in CS-224, the early labs. So we need a mux to cleanly choose this one or this one. So I'll have a little thing here saying memory to register M. And if the answer is no, it means ALU to register. Yeah, memory to register M, ALU to register M. So we choose, and it goes to right here on the input bus, and we write it to where? The RT register, exactly. So the destination bits need to say put it in the RT. Okay, so what are we doing here? We're incrementally, ilave, building ourselves a data path that can right now do all the R types, some I type immediates, and now I type load. Okay. Tell me what you think is going to change if I'm going to do a store. Store says calculate a memory address, that's very nice, and take something out of your register file and put it into memory when the clock comes. So I'll have the right signal be chosen. All I'm missing is just a connection from here to here. I got to get it out of this second on RT, and please bring it here. And you'll see that on the next slide. Not much else will change for the store word. Okay, here we go. So store word says, use this and this to calculate the address. There we are. So that's same, that's same, that's same. Look what changed. Instead of memory being on the right side and loading into register, it's registers on the right side, loads into memory. That's the only difference. So the value that I get out from register file using RT as the second operand goes to memory. So how am I going to do that? Beep. One red line. Got it? The RS value comes out here, the RT value comes out here, and that's the one you put into data memory. So writing wasn't very much different than reading. It just needed a place to get the data in. We already had a way to get the address to it. Now we got to get a way to get the data to it. And on the clock edge, it'll write. Tell me how many sequential storage elements you see up there now. Has this got a clock to it? Does it store anything? Sure does. That's one. Does this store anything? Does this store anything? Does this store anything? Does this store anything? Two. Mux no. So I've got two sequential storage elements. One we call register storage, one we call data memory storage. Memory m, register m. Both can be written to, both can be read from. Those are our two possibilities to store anything. That's why in the pseudocode, I forced you to be explicit and not just name your variables n. If it's in register, it's called nreg. If it's in memory, it's bracket of nreg. Yeah? You got to locate where the data is going to be. In high-level languages, you don't have to promise where it's going to be. It's just called n, and I add 1 to it. But in low-level languages, you got to know, is it here or is it there? It can't be in both. If it's n, it's here or it's there. We don't have multiple copies. Okay, so that's why your assembly language and even your pseudocode needs to be explicit on where is the data located. There's only two places the data can be. Are we good? What was there? Sinem? Okan? Okan, I'm sorry, but 2 out of 3 outvotes you. Beton Yok. All right, let's go on. Now we'll look at branch. Okay, the branch is an I-type, but it does something very different. We already mentioned that branch does not change any values in register. In fact, look here. Fetch it. Subtract the 2 and create something called condition. And if condition equals 0, then the new PC value is the old PC plus 4 plus all this. And if it's not, it's just the old PC plus 4. So only thing we're changing is the PC value. We do not change anything in register. So the PC is going to either get loaded with a very different address or a slightly different address. We either take the branch or we don't take the branch. I was talking to you about that at the break. What kind of hardware do you think we're going to need for that? Well, we're going to have the ability to subtract, and we're going to have the ability to change the PC. Some hardware to change the PC. Right now, the only hardware you saw for PC always adds 4. So that's the part that's going to have to change. And it's going to have to get its information from the data path. Because subtracting happens in the data path, and our ALU is going to tell us if the difference is 0 or not. Let's have a look here. Whoa, a big blue bubble, which is not the data path. See our data path over here? Okay, so all we're getting from our data path now, all we're getting is a signal called 0. It's coming out of the ALU. So we got what we needed, did the subtraction. Here they were, the 2 register values. We subtracted them. And the only thing we're interested in is that 0 signal, because it's going to tell this whole logic, do I change PC to be PC plus 4? Or do I change PC to be PC plus 4 plus the sign extended immediate value? Yanni, do I take the jump? And you can see that the immediate comes here. And the branch signal comes here, and the 0 signal comes here. And with that information, I can take PC and figure out what the next PC needs to be. It's either going to be that plus 4, because this told me don't take the branch, or it's going to be that plus 4 plus the sign extended version of this multiplied by 4, because this told me to do take the branch. Is that okay? Now, if this is BEQ, and this is 1, do I take the branch? This is BEQ and this is 1. Yeah. It means their FARC was 0, therefore they're equivalent, therefore they're equal, therefore take the branch. If this is BNE and this is 0, do I take the branch? Yeah. If this is BEQ and this is 0, do I take the branch? If this is BNE and this is 1, do I take the branch? No. Okay, we got it figured out now. So what does this logic have to be able to do? Take that, multiply it by 4, sign extended, and add it to this plus 4. It has to be able to have some hardware inside it to do that. That's all there is. That's how you determine the next value of the PC. So is that data path? No. It's in an area of, as it says, more detail to come. It's kind of like address, next address control. not really properly Datapath itself. So let's talk about this next address. Oh, don't talk about this next address control. Let's answer your question.
Why do we use RT minus RS instead of end functionality of ALU?
Why do we subtract them?
Yeah.
To find out if they're equal? You got another idea?
Last semester we called them end functionality to our LAU implementation.
Yeah, we could exclusive OR them together. And if all the bits were the same, the exclusive ORing will all give 0. If any are different, then it'll give a 1. We could do that too. We could exclusive OR them or we could subtract them.
Which one is faster?
Same. No difference in speed at all. So, okay. So they're both a fraction of a clock cycle. ALU, everybody can see here, obviously ALU cannot take the whole clock cycle because I've got to do what? Get stuff out of here, do stuff in here, and get it back in here all in one clock cycle. So I've got, delays, and so this has to be a fraction of a clock cycle. So we make it as fast as we can, and that determines our clock. All right, let's look at this next address business for branching, and then you can imagine that it'll just continue right into jumping as well. So we're almost finished. The PC is byte addressed in the instruction memory, okay? So sequentially, you want to take the old PC and add 4 and make the new PC, because it's 4 bytes later is the next instruction. And so branching would do this for us, okay? And that's when you think about byte addressing. Instructions are 4 bytes long, and therefore the 2 least significant bits are always going to be 0, 0, aren't they? The 2 least significant bits of an instruction address are always going to be 0, 0. And when you add 4 to it, it's going to stay 0, 0. You never change the 2 least significant bits. So why store them? Why have a 32-bit adder? Why not shrink down to the 30 interesting bits and get rid of the 2 0 bits? There's no reason to have the hardware to keep those 2 least significant bits if they're always 0 and never can be anything else. So we could simplify our hardware by going to a 30-bit PC. And so now what would happen is if we're sequentially, we'd say PC plus 1 becomes the high 30 bits of my new PC. And the last 2 bits are always 0. So we add 1 to the instruction address instead of adding 4 to the byte address. And when branching, it would change the branching as well. Don't have to shift here or multiply by 4. Don't have to add 4 here. It's this plus 1 plus the sign extended immediate. So now everybody sees that the sign extended immediate is not how many bytes to go forward or backward. It's how many words to go forward or backward. Everybody see that? Yeah, it's the FARC in words, not in bytes. Okay. So that will simplify our hardware a little bit. So let's go to now a 30-bit PC and an adder that adds 1, which we have a fancy name for. What's an adder that always adds 1 called? Incrementer. A little bit simpler here. Okay. And let's have everything be a 30-bit bus. See all those 30-bit buses? And so now my sign extender takes the immediate value and sign extends it into a 30-bit thing. And let's see how we go to the sequential next address. Well, PC plus 1, that's my sequential next address right there. And if I choose it, that becomes my next PC. So choosing this one is going sequentially. So I guess you could say choosing this one is taking the branch. How does it compute taking the branch? PC plus 1 plus the sign extended is the branch address. There's the sequential address. There's the branch address. We choose which one to take by this. Am I branching BEQ and is the value 0? Yes, take it. Yes, take it. Otherwise, don't take it. Are we understanding that? It's logic in hardware. That's why we call the course, digital logic. It's logic in hardware using gates and selectors. Okay, so that's our circuitry to implement the address portion of branching. Now the subtraction and where this came from, those have to happen, of course, in the data path. That's how branch addresses are calculated. For the BEQ, we didn't do the BNE. You would have another one of these and an OR for that. Let's go on. Now, if you want to have slow, small next instruction fetch logic, you do this. And the reason it's slow is because kaboom, kaboom, kaboom. We've got multiplexing followed by adding, and you have to wait for the branch and zero signals. We can't start the address addition until the ALU zero signal comes. In other words, until this comes, which comes out of the ALU, we can't begin this addition. And addition usually is much slower than just multiplexing. And if you want to make it, that was the slow, small one, and this is the fast, expensive one. Why is this expensive? And why is this cheap? Look at the two. Yeah, it's got two adders in it, two 30-bit adders. Why do they call it fast? Because the additions are all done, and all we're waiting is for the ALU to please tell me is it 0 or not, and we finish up. See, the slow stuff is done first while the ALU is doing its work. It's parallel work. This down here in the ALU is creating this as this is creating, so we're ready to go here. But in the other one, the slow one, oh, well, first the ALU has to figure out if it's 0 or not in a long, big calculation, and then that allows us to decide what we're going to calculate here. So we've got an addition after the ALU as opposed to in parallel with the ALU. So that's going to be small and slow. The other one's going to be expensive and fast. Oh, we didn't get to the jump. Okan Kazanda. All right, so we'll pick up with the jump instruction and continue this discussion on Friday. So see you Friday.